All right, so here we are at the rational functions. So we're going to start looking into learning about the rational functions. So as a must, rational functions, all of these rational functions we're about to learn must be learned after you have learned about the polynomial functions. So if you haven't learned about the polynomial functions, I highly recommend that you exit out of this video lesson right here and go back and learn thoroughly about the polynomial functions that I have had a thorough and in-depth lecture there. Okay, and then in addition to that, it is a must that at this point you must know what a function is, and you must know that any function has a graph, and as well as you also must know that that skill how to find domain of a function. Okay, and so I've had all of that once again in separate video lectures right there, and that was delivered prior to looking at this particular topic here. Okay, but other than that, let's dive in and look at what rational functions. And particularly, let's start out by looking at what a rational function is. All right. And so now, to maximize my board space right here, I am going to erase the topic title. So, quite unlike the polynomial functions, because there were a lot of introductory ideas with the polynomial functions. So for any instructor, it's a huge challenge to teach the polynomials in terms of, especially to teach about the polynomials at a pre-calculus level, because the amount of details are really just a lot, and it's really challenging for any instructor to teach the polynomial functions at the level where, you know, how much we have to filter out, where we need to, for instructors, we need to decide how much we filter out and how much is worth it to deliver at your level. But now when it comes to rational functions, then thankfully the content we're about to learn here in this lecture does indeed have a very definite content. So whatever details learned here is very standard. You're going to find it in my lecture, outside of my lecture, you will find it in any standard textbook, for pre-calculus. Okay, so that's a good sign, because we have a clear understanding of what we're going to be covering. Okay, so I'm going to start out with introducing what a rational function is first, and then we're going to start going through the process of looking at the different details about the rational function. But again, admittedly, that allow me to have my own way to organize and order these different subtopics about rational functions in a certain order that I feel best for the learning of my students and the viewers who are viewing this lesson. Okay, so let me introduce a few functions, and I will start getting into the idea of what a rational function is. All right, so let's look at something like this. Simply, I have how about 2x minus 1. Okay, and dividing that by an x squared plus 4x plus 5, for example. Okay, that's one function, and we can call that a function r of x. All right. I can also come up out of my own creativity with a function as following. How about q of x, and I can come up with that as an x squared plus 4x minus 1, and dividing that by x squared minus 2x plus 1. Okay, I can come up with another function. So how about, let me create a quick little column right here to separate out another space right there. So I can call that f of x to be another function, and then how about as simple as 1 over x. And this one here is indeed right from our toolkit functions. And then I can look at another one being, let's say, a p of x, and really naming it, the function is just any letter in our choice. And even these variables right here, we can call that any variable's name, but just for simplicity, I just stay with the tradition using x as the input variable. Okay, so p of x here, I'm going to call that, how about x cubed minus 5x plus 1, all right, and then divided by x plus 4. Okay, so now as I have written down about 4 functions, and these came out completely from my my own creativity. So believe me, once I erase this, likely I will forget about these functions because they're just any random selection that I've made out of my own creativity right here. But now at least with these random functions that I came up with and put it on the board right here, they have one thing in common. Okay? They have one thing in common, and so now allow me to write to pinpoint that common thing. That common thing they have in common, actually a couple of common things, okay, that they all have in common. And then as I finish pinpoint them out, then we're gonna recognize, from that we're gonna push into a formal understanding of what a rational function is. Okay, so just right at observing this first function, the order of x right here, what caught my attention here is a fraction. Yes, admittedly, numerator and denominator, they're all large expressions. Like say we have a 2x minus 1 over, and then the x squared plus 4x plus 5. That's a large expression in the denominator, a large expression in the numerator. But what caught my attention now, okay, most or mainly what caught my attention here is a fraction. It's a fraction. Okay, something on top, something at the bottom. All right, and then moving on to the q of x, I have on the board here, I see another one but similar feature in the same main feature over here. It's a fraction here. The expressions in the numerator and the denominator are even larger. Okay, I have a more complicated looking expression in the numerator, and even a more complicated, it's actually about the same complexity with the denominator here compared with r of x. But now what mainly caught my attention again is that it's a fraction again. So that's the one common thing these two functions r of x and q of x share in common. They both have in common. So we recognize a fraction. So what about the f of x? Right here in the board right here on the board, right in front of everyone. Okay, it's a fraction again. But then the expression here, the numerator and denominator are a lot simpler, but in the end it's a fraction. All right, it's a fraction. And then here, once again, it's a fraction. Okay, some expression in the numerator, some other expression in the denominator. Okay. And so now, the first thing that caught our attention, any of these is a fraction. Okay, so let's pinpoint down immediately that first feature we recognize, and then from there we're gonna push into a formal understanding. So what I noticed throughout throughout all the four quick examples there, any one of them is a fraction. Okay, that's the number one understanding. All right, any one of them. So allow me to use a short way of interpreting it. A function means just a fraction, just means any one of those functions we've seen on the other board was a fraction. Okay, any one of them. There is another common feature among all of those I brought up on the other board, that not as easily seen as being a fraction here, not as easily attention catching, okay, not as easily attention catching as this feature over here, but it's also one more thing that's common among all those four functions right there. So let's look back. All right, and the reason I mentioned earlier right at the beginning of this lesson is that we must learn about rational function after you have successfully learned about the polynomial functions, because now if you focus, let's look right here at this particular function, this expression right here, this fraction for now. Some expression in the numerator, some expression in the denominator. But if we're now looking individually at each of these components right here, the numerator and the denominator, this is in what we are now familiar with. This is a polynomial. Okay, and the denominator is also a polynomial. All right, so the first function I noticed here, aside from being a fraction, aside from having a fraction, okay, then I noticed I noticed that both numerator and denominator are all polynomials. It's a polynomials. I'm not saying that the two polynomials are the same polynomials or anything like that. There are not even the same degrees here. Okay, and we will get even further into that. But now one thing they have, both numerator and denominator of this fraction are all polynomials. Okay, it's a polynomial. Here is the degree 2 polynomial. In our language, we are already familiar with. This is a degree 1 polynomial. In that terminology, we are already familiar with. All right, and so now I recognize there are two polynomials here in the numerator and in the denominator for this first function, in this first fraction. Okay, and so now let's carefully investigate the next one here, q of x. Is that the same for q of x? I have a polynomial in the numerator, and I also have a polynomial in the denominator. Okay, polynomial here in this fraction. So that's common with. I'm not saying any of these are looking like the other one. I'm not saying any of these is looking like the other ones. Okay, but again, what I'm seeing here is it's a fraction, and both numerator and denominator are polynomials. Okay. What about the next one here? It's a fraction, admittedly. We agree with that. And now both numerator and denominator, it's a little bit dangerous in a sense that each one of these is surprisingly shorter than the other ones I've written here. But in the end, it's a constant one, but constant in our understanding at this point, constant function is classified as a polynomial. Okay, so it's a polynomial over a polynomial. Okay, and now even for short, I'll just call it's a poly. And it's a poly. Okay, it's a polynomial. And that's just a shorthand writing of mine to save time. Okay, so three functions. They all have that common thing right there. Aside from being a fraction, they all have a polynomial in the numerator and in the denominator as well. Okay, the same with that. So what about the last one here on my list right here? P of x, see, it's a fraction, but aside from that, polynomial over polynomial. Polynomial over polynomial. All right, so see, polynomial, this is a degree 3 polynomial, and this is degree 1 polynomial. All right, so now I'm ready to pinpoint that feature number 2 right here on this board with the red ink right here. So the first feature we saw earlier that immediately caught anyone's attention was that any of those functions is in the form of a fraction. Okay, and then the number 2 that I just now have to explain a little more details. We have, so how about I would say both the numerator, because in the word of fraction, numerator is a term right there. Okay, the top part is numerator, the bottom part the denominator, and there's the fraction bar in the middle, the stack in the middle between the two. Okay, so the numerator, both numerator and denominator. Okay, both of those are polynomials. All right, so that's one thing now we all recognize throughout all of these functions right here. Okay, and so now, ladies and gentlemen, these two requirements right here, these two requirements together make up what's so-called the rational functions. Okay, so any of those functions we have seen on the board, okay, any of these functions we have seen that we saw on this board right here, any of these, we now call them, these are the rational functions. Okay, rational function. They are functions, and they are rational functions. That's specifically as a classification of these functions right here. Okay, so now over years, anytime when I'm teaching a pre-calculus class and get into this particular topic, either the class is a face-to-face or hybrid or online or whatsoever, where I have to deliver through a video lecture right here, I always I always lead my student under this approach right here to hopefully click with my students. But this term rational right here, an easy way to remember, it has that prefix, and allow me to underline that prefix right there. It's just something I pinpoint to keep it easy, to make it easy to remember for students about the way how the function is named, and it has a whole intention behind the scene right here. See, so that prefix, ratio, what does that refer to? Okay, have a minute to think about that. That particular prefix right there rings a bell that, hey, the kind of function we're about to look at, anytime we hear the term rational function, okay, anytime we hear that term rational function, that prefix here should ring to our ear, or just once the name of the function is rang to our ear, that particular prefix right there should bring to our attention that immediately it's a fraction, because ratio. So the function has to first thing be a fraction. All right, be a fraction. That's the first thing. But then, aside from that, aside from being simply just a fraction, aside from being just a ratio, okay, then each component has to be, each one of the two components has to be a polynomial, or another way of saying both numerator and denominator are all polynomials. Okay, both numerator and denominator are all polynomials. So now this is, again, because this lecture here is so connected with the polynomial we have learned, and especially it is a must that we learn this lesson after, and highly recommended that we learn this immediately after you finish learning about the polynomials. So allow me to actually assume that you already, once you are continuing with this lesson right here, allow me to assume that you are already fluent with your skills in terms of the polynomials, or at least be fluent with the way how we communicate about the terms of the polynomials. So now, back in my lectures about the polynomials, I brought in a few examples where the functions were not polynomials. For example, well, square root functions. They are power functions, but specifically as polynomial, they are not polynomials. Okay, and then but now if I'm setting up a function as following: square root of x over cube root of x plus 5. It has fraction. The reason I brought this up, because functions like this exist out there. Function like this exists out there, and it also has fraction. Okay, so a lot of times students, after seeing this particular function given to them or brought to their attention, they rushly conclude that, they rushly believe that this is a rational function. Nope, it's not. So I have to highlight, this is not a rational function. Okay, so why is that? So let me briefly explain. So it has ratio, it has that fraction component, admittedly, but it failed having both numerator and denominator being polynomial. As a matter of fact, this function square root of x was not classified. So according to my argument, my logical reasoning back in the polynomial lecture, then I made my reason about how this function here, yes, it's a power function, but it's not a polynomial. And so as long as any one of these numerator and denominator fails being a polynomial, your fraction is not, or does not qualify yet to be a rational function. And then as a matter of fact, with this function here, both numerator and denominators fail to be polynomial. So this whole thing here is not a rational function. Okay? We will see this kind of function, function later on, but and right now I'm introducing this a little early, but we will get to that in the later part of the quarter of the learning term here. But say I have a 2 to the x over 3 to the x minus 5. Okay, it's another function. So now also allow me to erase this earlier quick example I brought up. So now this function here, it's a function. Okay, and we can name that a f of x or whatever, or g of x or h of x, however you want to call it, that as a function. It's a function. And then again, immediately it caught our attention that this function has a fraction nature. So it passed that requirement. Okay, the function here passed that requirement. However, this function still fails to be a rational function. So now, sadly, yes, having a fraction nature right there, but it's not a rational function. So why is that? Again, in my lecture where I started explaining about the polynomials, any one of these two functions, any one of the numerator and denominator in this particular function here, in this particular fraction, is not a polynomial. 2 to the x, later on we will get specifically into that class of function. Okay, but 2 to the x, well, for you to know right now, 2 to the x is called an exponential function, but it's not even a power function. Okay, so we don't classify that as a polynomial. And the same with the 3 to the x minus 5 right here. The entire denominator here is not a polynomial function. So in other words, this whole function here, this entire rule here, even though set up as a fraction, but in the end it failed to be a rational function. So it's not a rational function simply because both of these components here are non-polynomials. All right, so I brought up a few quick examples here. So the second requirement here, see, a lot of time, admittedly, and the reason I wrote that down first, because a lot of time, admittedly, what caught our attention easily, and first thing, when you're looking at a rational function, is that it has a fraction nature, and so it catches our attention easily. And that should be feature number one to nail that down, to keep in mind. But then, as a further and also important requirement, okay, as a second requirement as important as the first one, both numerator and denominator must be polynomials. So even in red ink, I still want to underline this. They both have to be polynomials. So as long as any one of the two components here fails to be a polynomial, your overall fraction, unfortunately, does not qualify to be a rational function. All right, so now at this point, and this is the only criteria to determine where it is or what it is to be a rational function, and what it is or when it is not a rational function. Okay, and so yes, this is really enough to know what a rational function is, but of course, let's give it a formal definition of what a rational function is. Okay, so I am going to write down, after erasing this board, I am going to write down the definition on this board, and then we're going to head back to the other board for some actual example. All right, so now as far as definition. All right. And when it gets to this, allow me to have my own freedom to word the definition of a rational function in my own style. Okay, it may be the same with the way being worded in some textbooks you may find out there, but once again, it's just my own style of wording the definition of this rational function. So a rational function okay, a rational function or any rational function is a function in the form, okay, how about if we want to call that f of x, then it has to be in the form some p of x over q of x. See, immediately it displays the fraction nature. So first thing, it has to be in the form of a something over something. That's what's the first. That's consistent with the first feature I was pointing out earlier. Okay, so it has to be in the form of a function over another function. So that's why I have some p of x over q of x, some function over another function. And then, but then that's not the only requirements. There has to be another requirement. So it has to be in the form of a p of x over a q of x, where both So P of x in this fraction here is the numerator, needless to say, and Q of x is the denominator. So allow me to save the wording, the lengthy wording. Okay, so now I'm going to just get straight to the point where P of x and Q of x are both polynomials. All right, one nice and short definition, but it represents all different angles, all different aspects of a rational function. Okay, and so that is what it is right there. That is what it is. So a rational function, anytime looking at a rational function, it has to be first thing in line right here. It has to be in the form of a function over a function. It's indicating it's a fraction overall. And then aside from being a fraction, each component, P and Q here, are both polynomials. Nothing about the degrees. The degrees has nothing to do. The degrees is the property that belongs to each of these components of your each of these polynomials in your rational function. Okay, and then we're going to study throughout our entire discussions about how the degrees individually on each one of these parts change the shapes of our graph, change the behavior of our rational function. But in the end, in the formal definition here, it has nothing to do with the degree. Okay, so a rational function is simply in the form of a fraction of two polynomials. That's another way of putting it. But I don't want that definition to be too short in the way how I just verbalize it out. All right, so now let me take you into a formal example where we just learn that skills to identify any function given at us to be a rational function or not. Okay, and you're gonna be even shocked about how big this family of functions is. Okay, and you're gonna keep getting shocked as you opening your understanding to such a big family of functions like that. All right, so now let's head over to the other board and to get ready for that first example here. All right, so now we are at example 1 right here. Okay, so determine if each given function is a rational function. All right, determine if each given function is a rational function. Okay, and again, you are going to be amazed how big this family of functions is. This family of rational functions is. How big that is in terms of the amount of those functions out there. Now all of a sudden we realize they all belong to, a lot of those functions we've learned earlier belong to this family. Okay, so now needless to bring up those that are too easy. Okay, so now let me bring up a function as following. All right, so this one here, x cubed minus x squared plus 1. It's short, but it's showing enough, and it's getting a little dangerous because the numerator here has only one term. Okay, and you start feeling a little worried because the earlier one I brought up before we even got into the definition, then it's quite clear and we see the polynomials clearly, but here what this thing here in the denominator is a polynomial. Okay, so all we have to do now is to identify. So we have a fraction here clearly already. So all we have to do next is to identify whether each one of these being a polynomial or not. Okay, so x cubed, now in our experience up to this point, and provided that you have already learned about what a polynomial is, then x cubed is a polynomial. That's a polynomial. Okay, that's all we have to do. And really, this is not even the formal steps of the problem. It's just I'm writing down the thought process. Okay, and so this problem right here usually does not appear as a written problem for instructor to collect from student submissions, because it's just too simple to the point that it's just all about in your thought process, how you can decide. Okay? So the bottom one here is also a polynomial that you are now well aware of that. All right, polynomial. So it's a fraction clearly. Both top and bottom are polynomial. Yes, so now you can call that, so now this one here, I'm going to put a check here. Yes, it's a rational function. All right, let's move on to the next one. And so sometimes I can even call this the p of x to make it consistent with the definition. And this bottom one here is the q of x. So likely that in the next few problems, I'm going to switch style by first indicating it. Once we recognize the fraction nature, I'm going to indicate where it is to be the q of x, the p of x, or where it is to be the q of x. Okay, so, but this one here qualifies to be a rational function, and it is now a rational function officially. All right, let's look at part B of the example. All right, so part B of the example. How about I'm going to look at f of x to be, and I have explained, you have seen this earlier, the 1 over x right here. So needless to say that anymore, but now how about just a 5 over x squared? A 5 over x squared. So in the numerator, we still see a fraction. We're still seeing a fraction. Okay? So now clearly we can label this as p of x, and this is q of x in the denominator. Okay? And then so clearly it's already a fraction, p of x over q of x. Now is this polynomial? Okay, that's the next step right there. And is this a polynomial? Okay? So I put check here, I put check there. That's another style of completing your checklist for being a rational function. How's that? Okay, so now in that way, yes, the reason I see this 5 here is a polynomial because the numerator here is a constant. The numerator is a constant, and we already learned from previous lecture, from our previous understanding, that a constant is well classified as a polynomial, okay, as one among the polynomials. So that's why, so now in the numerator it's simply just a constant, but it is a polynomial. And now we see fraction, and clearly this is a one single term polynomial. So yes, the whole thing here now, polynomial on top, polynomial at the bottom. That's why I'm putting the 2 checks. So this whole thing here now, I'm using a big red check like that. It's a polynomial. I mean, it's a rational function. This red check right there, it's a rational function. All right. Let's look at the next one. I can look at, how about let me challenge your understanding a little bit. So now let's look at f of x equals just simply x squared plus 1. Just that. All right. Have a moment to think about. Give some thought into it. It's not an FYT. Okay? But before I really roll into giving out all the reasonings right here, I want viewers, I want students viewing this lesson to have some deep thought about this function. Well, you may say it's a polynomial. You may say it's a polynomial. I agree. But now let me start amazing let me start shocking your attention here. In algebra, even though we're seeing one simple expression, we always have our choice to re-express that as a fraction. Say, for example, we've been knowing for years that 2, which is one usual number as usual in its most natural sense, 2, but now with a little more advanced understanding in math, 2, we always have our choice to write it as a 2 over 1. Now we display that fraction nature. And that's what I'm about to do here. So even though right at start, anyone at plain sight is just seeing this as a polynomial, because I understand very clearly, we don't see the fraction nature right here. Okay, so we thought for once that it fails being it fails being a rational function, but now indeed we can purposely write it as an over 1. And now so all of a sudden we found out that, hey, this is indeed now in fraction form. It passed the first requirements being in the form of a p of x over a q of x. All right, because a lot of time that is also one part that got people hung up right there. That is, anytime they don't see the fraction, they thought that the function is done, and pass that function. Okay, let it go. It's not a rational. But now, if we're looking a little more carefully, we can always purposely put it over 1 right here. Now we display the fraction nature. So now clearly it's a p of x here. This is a q of x, and they are both polynomials. I should have written that term out. It's a polynomial, and it's a polynomial. Okay, it passed both requirements. We can show the fraction nature of that function, and both components, both p and q, are all polynomials. Okay, so I'm going to put a big red check here for this function. Yes, the function, so it's never contradicting with what we learned before, and it never contradicts with what you thought it was earlier. It is still a polynomial. But now further, it's also understood as a rational. Okay? So yes, this thing is also a rational. So now put a good remark here. Any polynomial at this point, any polynomial that we used to know, right, is a rational function. Because we can always put it over 1. Okay, any polynomial is a rational function. And this is what I was talking about right there, that you're going to be amazed how big this family of rational functions is. Because all of a sudden, once we've learned it, we're learning that those functions we've learned, the whole lectures about all the polynomials that I've spent so much time looking into the in-depth details right there. But any of those now can be just a member or a subfamily of this bigger family, the rational functions. All right, so that's a big star remark right there, that any polynomial is a rational function. I agree with that. All right, so now let's look at another one. All right, so the one I'm about to show on the board here, to write on the board, part D. So now, absolute value of x, your common, your toolkit functions, one among your toolkit functions here. This quite common, quite the familiar function right here. F of x equals absolute value of x. We've seen this function before, okay? And now just right after picking up that experience from part C, somebody can quickly think of that same experience right there. We can purposely put this over 1. Yes, I'm not objecting that. Okay, if any of my students is telling me that, hey, why don't we put that over 1? Yes, mathematically it's completely legal. Algebraically it's completely legal. So yes, I see fraction, but now this function here, indeed, ladies and gentlemen, this overall function, even though we have already put that in fraction form, it still fails being a rational. It still fails being a rational. So why is that? Because now, you see, the denominator, yes, maybe the denominator q of x here is a polynomial. Okay, maybe it passed the denominator to be a polynomial. But the numerator here, this p of x right here, okay, being a polynomial, okay, it's not. And so just like that, yes, even though we have fraction here, but as long as one of the two components here fails to be polynomial, the whole function fails being rational. So in other words, this function is not a rational function. All right, so let's make that big title here for that function. It's not a rational function. So this is one function that's not classified as a rational. Okay. Not a rational function. All right, let's look at another one. All right, so in part E right here, now I can write down the following function. How about f of x equals, I have a fraction bar, I'm about to draw a fraction bar. How about x to the 3/2 power minus 2, okay, and I'm dividing that by x to the 5/2 and then plus x to the 2/3 plus 1. Okay, so clearly it has fraction. And then there's some p of x, there's some q of x. So yes, this is a p of x right here. Yes, this is a q of x right there. Just some two functions, being one of them is in the numerator, one of them is in the denominator. But is this one here polynomial? Is this one here polynomial in the denominator? They both fail being polynomial. Okay, because yes, this is a power function here, but the power is not the power here. Any one of the powers here is not an integer power. So it fails being, any one of these fails being a polynomial, because recall for yourself from our lecture about polynomial, we want to specifically focus on those, being a polynomials, we want to focus on those power functions where the powers are integer values, okay? Non-negative integer values. All right, and so now that is this whole thing right here, that is not, okay, that is not a rational function. All right, that is not a rational function. All right, and so now and the last one on my list here for anyone. Okay, we will not see this kind of functions here at our level here, but just want to let you know they exist out there. Okay, and there will be the course immediately after this course, right before calculus, that you will learn these functions. Okay, so allow me to just briefly write them out down right there, and then, you know, in the very next course that you're gonna take, right before calculus, right before you arrive at calculus. As a matter of fact, the next course is called the pre-calculus 2, the second components of pre-calculus. You will learn intensively about these kind of functions. So it's just a little bit ahead of time. But for you to realize more and more functions out there that, hey, a lot of times we have functions in the form of a fraction. But let's find out. So how about f of x equals some? Okay, so here, ladies and gentlemen, your calculus, your pre-calc 2 will have this kind of function. How about there's a function that's, we don't have to know what rule that is yet. It's some rule that we call the sine rule. Sine of x over cosine of x. These are, like I said, at first sight it's, what is this? But sine is an operation, and you will learn that formally at your pre-calc 2 course like that. But it's sine of x itself is a function. This is also a function. Okay, so one function over another function right here. Yes, as a matter of fact, these are the trigonometry functions. And like I said, you will spend your entire quarter learning about these functions at pre-calculus 2. That course right before the formal calculus course. But then, in the end, the whole thing here is a fraction. I agree, the fraction between two trig functions. But any one of these is clearly not a polynomial. We don't even see any powers here. All right, so in that way, this is not polynomial. And then at the bottom here, not polynomial. All right, see, I purposely brought these in. It's not to, it's not to make anyone feeling shocked or anything like that, but it's just simply to indicate, to emphasize the fact that anytime that we're staying away from the polynomials, but still having a fraction, then the whole function here fails to be a rational. So this one here clearly is not a rational function. All right. All right. So at this point, we have seen enough of those problems where I've shown and where I've emphasized that we only stay with our two main requirements, that it gotta be, in order to be a rational function, it gotta be a fraction and it gotta be polynomials on both top and bottom right there. That's how it qualifies. The function can qualify to be a rational. And then here are some examples where it fails one of the two requirements. Okay, and so at this point right here, pretty much requirement number 1 is hard to fail. It's just another remark that, let me swing back to the formal definition. Requirement number 1, that we have to see a fraction nature of our function. So this requirement is almost impossible to fail. Really, it's impossible to fail, because in some of the example I brought up earlier, then we can purposely write, even with the one single number, we can purposely put it as a fraction over 1. And so in that way, really, I use the term nearly impossible just because I never verified to myself that is there any possibility out there that some function we cannot write as a fraction at all. But in the way how we see it, we can always put it over 1. And so failing this requirement is impossible. The requirement number 1 is impossible, mostly impossible to fail. So what most of the time that functions fail being a rational is that either one of the two here fails being a polynomial. Okay, so but that's just another detail as a remark right there for you to understand, to keep in mind, put that in your pocket reference as we go along with this journey on all of the rational functions, and on your journey of the rest of your journey in mathematics. All right. And so now, after leaving this here long enough, let's set out for ourselves an agreement together here for the rest of the lecture. Okay, because now we're done with looking at what it is for being a rational function. We're done with looking at what it is. But to make it fascinating for the rest of the lecture, and of course it's only fascinating when we restrict our attention to these rational functions right here. So we definitely want to see those kind of rational functions where, okay, so here's our focus. So allow me to write it in this improvised, informal way right here. So our focus here, this is what we focus. So as our focus, we want to focus on those rational where clearly p of x and so we focus on those rational functions where, how about, where q of x is other than a constant. Okay, we're gonna focus on those rational functions where q of x, the denominator, is other than just a constant. Meaning I'm talking about an actual polynomial other than just being a constant. Because, well, it's not that we're ruling out, but when it's a constant, then it's simply just really a polynomial. Okay, just think about an x squared plus 1 right here. What if the denominator is simply a constant like 5 right here? It's still a rational function, but something like this is not too fascinating, because we can now just, in that experience I have pointed out, a polynomial can also be a rational. So here, with a rational this way, we can purposely bring it back. We can purposely isolate it out as a polynomial. So it's now becoming a 1/5 times x to the square plus a 1/5 right here. So now seeing it's being a polynomial, then nothing fun about to look at this anymore. We're just repeating our understanding from polynomial. Okay, so we don't see much of the rational function nature in these things. Okay, even though it's still there, but it's just not fascinating anymore. So we just now, our focus here, we're going to look at those rational functions where the denominator is other than a constant. Okay, and meaning something like this. We're going to be working with, if it's an x squared plus 1, but over x minus 1, something like this will deserve our attention. Okay, or even just the numerator can be a constant, and then we have x squared minus 5x plus 6, for example. Something like this will deserve our attention to look at. You may see a function like this throughout our examples that we're going to be going through. Okay, but these are all what I so-called rational functions where the denominator is other than just a constant. That's what I meant again, and that's what we want to focus to, because that's where all the fun, this is where it creates all of the fascinating learning features for us to go through. Okay. All right, so now that we have learned about what it is to be a rational function, so now it's time to look at the first important feature of a rational function. We're going to learn how to find the domain of a rational function. So I got to make it clear at this point that some lecturers, when I talked about a specific family of function, I may not mention at all about what the domain of a function is, of that kind of function is. That's simply because, so one thing I got to make it clear. The domain is now, after you've learned about any function has a domain, then what I want to make it clear is that any function has for itself a domain. Okay, it's just a property that by default it will come along with that function. Okay, but then throughout my lectures prior to this particular lecture over here, some lecture when I was particularly talking about some other kind of functions other than this rational function class right here, then I might have not mentioned about domains at all, or didn't even get to any problems about finding the domain of those functions. That was because with those functions the domain were easy to find. Okay, and then here in this kind of function, due to the nature of the function itself, it's such a fascinating world to find the domain. Okay, and so for this part of the lecture here, we are not going to learn about what a domain is, because we've already learned all that. We have already understood clearly what the domain of a function is. But now, specifically for the rational function, we want to learn the technique. We want to learn the solid methods of how to find the domain, okay, for any rational function. And particularly, any rational function will have a different domain. It all depends. And that's why we need to learn one solid method of how to find that. Okay, it's not like one domain that works for all rational functions. Okay, and so yes, primarily we're now focused to learning how to find the domain of a rational function. All right, so we want to find the domain of a rational function. This is a subtopic, okay, throughout the entire lecture we're going through right here, that we're learning about everything about every detail about the rational functions. Okay, so now there was a reason why I brought up that remark over there. There was a reason why I brought up that generalization on the other board, that we want to, for our discussion here in this lecture, we specifically want to focus on those functions where, on those rational functions where the denominator is something other than just a constant. For example, I mentioned about this function right here, the x squared plus 1 over x minus 1. So the denominator here is other than just a constant, okay? Or something like this. The numerator and then the denominator, this is q of x, is other than a constant. So the reason I mentioned this, reason I specifically turn our focus and lead your focus to this kind of rational function where the denominator is other than a constant, simply because this is where it creates all that fascinating learning details for us about how we can find the domain of a rational function. Okay? And so in this way, what's in those functions, the rational where the denominator is other than a constant. Because now when your rational function in a form of a p of x over a q of x, where the denominator is other than a constant, and that means now we must realize again, in the end, a rational function is a fraction. And so now once we specifically focus on that kind of rational functions where the denominator is other than a constant, then we have to, doesn't matter how we work, doesn't matter when we work and how we work and what we do to the rational function, we must always ensure, and we must always watch out to ensure that the denominator must be non-zero. It's just the nature of fraction. It's naturally come out, this thing here, this requirement here comes out naturally as a requirement of having a fraction. Okay, so now let me really clarify my idea earlier. If we had our rational function simply as an x squared plus 1 over 1, a constant right here, then the denominator being a constant here was already a constant clearly other than 0. So there's not much to talk about the domain, and that is the reason why if we keep looking at rational functions like this, we might ignore the fact, we might accidentally ignore the fact that we need to consider the domain carefully. Okay, and so now at the bottom line here, being a fraction in our rational function, being clearly a fraction in our rational function, where the denominator can be an expression other than a constant. So depending on the value of this expression right here, this denominator can change to different value. That is the reason why we have to always ensure, we must ensure q of x, the denominator, is other than 0. All right, so now in that way, that's the highlight the highlighted central theme of this work, finding the domain of any rational function. Anytime we're working with the rational function, we must ensure that the denominator is other than 0. The value of the denominator other than 0. Okay, and so that's the major goal right here that we are trying to reach, the major requirements. But now, in order to meet this requirement, that we must ensure the denominator being other than 0. Then how can we ensure this? How can we ensure the denominator is other than 0? And so now, formally as a method, now you have seen this method earlier in our discussion about the domain of a function, and we've had quite a few examples where our functions there came out from this family. But now let's specifically emphasize on that method because it will meet our need here for the rational functions. Okay, so now again, you're well aware that our denominator, our function here is a rational function having a denominator being other than a constant, being dependent on an input variable x like that. So the value here must be, the value in the denominator must be ensured to be other than 0. So in that way, to ensure the denominator being non-zero, here's the logic right here. We want to start out the method here. The idea here is we want to purposely let our denominator equal 0, and then from there we want to find the x value. We want to solve for x. Okay. Because here's the thing, again, of course, we want to ensure the denominator is non-zero. But to ensure this, one effective solution, one effective method is to purposely let the denominator equal 0. Okay? And then upon letting the denominator equal 0, we should be able to solve for or to find all the x values, maybe one or maybe a lot. Okay? Maybe one singular value for x, or a lot of values for x that satisfy the denominator equals 0. Those x values will eventually be regarded as the bad guys. Okay, so I also brought that idea back in our lesson about finding the domain. So these are the bad guys. We want to search for all the bad guys. And once we have done successfully finding all the bad guys right there, the domain of our rational function will be anywhere excluding these bad guys. Okay? So that's generally the method, right there, the solid method that we are about heading into. Okay, so right now I'm about to fire up a demo problem right there, a demonstration problem. It's not going to be a formal example yet. Okay, so allow me to use one of the example I brought up here. So I'm going to pick this particular one that came out from my own creativity right here. But this function, the denominator here, this rational function is having that denominator q of x is other than a constant. So let's look for the domain of this particular function. Okay. So now on my board, to demonstrate what I was saying about that method, so we purposely let the denominator equal 0, and then in that way we can search for the bad guys. So here, since it's not a formal example yet, allow me to just introduce the function as, hey, let's consider that function r of x equals x squared plus 1 divided by x minus 1. So now in our understanding of what a rational function is, then yes, we can see this as the p of x being a polynomial. The one in the denominator here is a q of x being a polynomial, and further it's other than a constant. Okay, so that means the reason I emphasize that because the value of the denominator here can change depending on what input x we're giving it. Okay, and so some input x may cause the denominator equals 0. And that's where it's bad for a fraction, for being a fraction. Okay, well, it's just a little bit of a side talk here, but you know, when I meet with my students face to face, okay, or even in other lectures when I'm leading an online class, eventually at some point I'll make this joke to my students that, you know, as long as we are human on earth, we will never know how to divide by 0. It's just the nature of the kind of math that human on earth to work with. Okay, and so we have tried, really historically, we have tried to, the mathematicians, all of our famous, well-known mathematicians throughout the entire history have tried to develop so many different techniques and so many different system of numbers to overcome the criteria, the crisis about failing to divide by 0, but we still cannot overcome that challenge. We still just can't divide by 0. We can't divide by 0. So in that way, so now back to this specific function right here. Now upon realizing that the denominator here is an expression other than a constant. Okay, so it's the value of this denominator can change depending on whichever input value that we're giving for x. So in that way, we must, as a goal, yes, let me remind that permanent requirements again, we must ensure that q of x, or now in this case specifically, our q of x is x minus 1, so we must ensure that x minus 1 as our denominator must be non-zero. That's one thing we must ensure. We want to always ensure the denominator is to be non-zero. But then, so yes, that's our goal. But now, effectively as a solution, effectively as a way, as a method to ensure this, then we're going to purposely start out by letting the denominator, in this case, one simple expression, x minus 1. We're going to purposely let that denominator as a polynomial. Now, right now, realize that this polynomial is a linear, it's a first degree polynomial. Okay? We're going to purposely let that first degree polynomial, our denominator here, equal to 0. Okay? And then once we let that, we're going to start solving for x. Okay? Because solving for x out of this, well, what we realize here from our past understanding, from the past courses, then this is just simply an equation. So solving for x from an equation just means we want to find the value or the values of x that satisfy this equality, this left-hand side expression to equal 0. Okay? But so now once we found the values for x, or once we have successfully solved this equation here, those values for x that satisfy this equation, we refer to them as the bad guy. Okay, so let's get to it. So now solving this equation, it's simple enough, and there is now at this point, if you're looking back at that lecture where I was going over all the details about the polynomials, then there was a reason why I spent a good significant amount of time reviewing. Okay, reviewing. I was teaching the new material, but I was also partly reviewing this concept right here because it's so vital. Okay, the concept in being able to solve a polynomial to equal 0. Okay, that concept right there, I was going quite intensive. I mean, quite in a good amount of review in our earlier lecture when I was going over the polynomials. So now with this, from our understanding, we're going to add 1 from both sides. Okay, and then that gives me x equals 1. All right, so for this equation, setting x minus 1 equals 0. And remember, just remind yourself where x minus 1 came from. It's the denominator of our rational function given here. So now this is just, well, we solved this equation, but this is not the answer to our domain. This is not our domain. Okay, I got to be clear. I've circled that in red ink right here. Now I have to highlight this. This is the bad guy right here. This is the bad guy that we have found. And once we have successfully solved this equation, sometimes there's only one bad guy, sometimes there are multiple bad guys, more than one bad guys. Solving our equation by setting the denominator equals 0 will help us search for all the bad guys. How many there are, we're going to be able to track them all down. Okay, so why do I call this the bad guy? Because this value x equals 1 will cause the denominator equals 0. That's why it's bad. Okay, so now what do we do with the bad guy right here? So with this guy being with this x value causing the denominator to equal 0, but then we want to ensure, our logic here is that we want to ensure the denominator is other than 0. And so that means now, logically speaking, we want our x value is anywhere not 1. Anywhere not 1. So now just think about the graph right here, or the line of numbers. All the x values there, 1 is somewhere on the line of number. Exactly in the middle or somewhere shifted to the right hand side or the left hand side, that's not important. 1 is just some value on the line of numbers right here. So we just take any values aside 1, or any value of x except 1. All right, so that shaded part right there, the two disconnected shaded parts are together our domain of the function. So now, formally speaking, in interval notation, now the domain of this function here is as following. We have an interval to the left of 1. That means it's anywhere between infinity, negative infinity, and 1. And we have another one between 1 and positive infinity. Okay, and now we take the union. So whatever I'm doing here with the interval notation, it's just familiar work that we have done quite sometimes in our earlier lectures when I was going over the domain, the concept of finding domain generally. Okay, so now this is the domain of this particular function, this particular rational function, x squared plus 1 over x minus 1. All right, so at this point, let me make one quick pinpoint. Let me quickly pinpoint this detail right here, and before we move on to the next one. But we completely, when we were looking for the domain of a rational function, nothing was done with the numerator at all. Nothing was done with the numerator at all. Everything we worked with was just in the denominator, because that's where all the likeliness of the trouble can come. Okay, that's all we have, all that likeliness of trouble to come right there. So the denominator, once we know that it's not what the denominator, once being other than a constant, then it can become a 0 right there. So our job here is to ensure the denominator is non-zero. All right, so that's how we found the domain. The method here is that we let the denominator as a polynomial, we let the denominator purposely equal 0, and then we could start solving for the values of x that cause our denominator to equal 0. And then we consider those values of x that we solve for the bad guy or the bad guys. Okay, and then our final domain is just anywhere that excluding anywhere except the bad guys. All right, and then we're gonna write that in interval notation. So let's do another demonstration problem right there before we get into formally an example. Okay. So now I'm getting on this board of mine right here, and I have left this here long enough. So let's now put that away. So I'm gonna use right here. I'm gonna use that other function where I creatively came up with to emphasize that we want to work with those rational functions where the denominator is other than a constant right here. So I'm gonna get into finding the domain of this rational function. Okay, and so now let's consider this function. How about I'm going to call it f of x to be 5 over x squared minus 5x plus 6. All right, so we have our rational function there. It's in a fraction form. Okay, ratio and top and bottom are both polynomials. And now furthermore, this denominator here, okay, this denominator here is other than just a constant. And that's why, once again, in that logical understanding, in that logical reasoning I made earlier, that we just want to ensure, because it's a function, because it's a fraction, and the denominator here can change value depending on whichever input value for x that we're giving it. And so that's why we need to ensure that our denominator, that's all we have to do. We need to ensure x squared minus 5x plus 6, our denominator, to be other than 0. That's our goal. All right, but then, so I emphasize this goal right here. But then, in order to achieve this goal, ensuring the denominator is other than 0, it's non-zero, then we're gonna purposely let our denominator x squared minus 5x. And notice again that this is indeed a polynomial. We want to purposely let our polynomial in the denominator equals 0. All right, and then from here we are going to solve for x. So the work is extremely similar to that other demo problem I brought up on the other board right there. Okay, but so this, now once we arrive at this equation ready to solve for x, then anyone viewing this lesson is going to realize, hey, wait a minute, this is a quadratic equation. Yes, I agree, and I admit, okay, but the point I would like to emphasize now is that, and I have done, again, I've done a good amount of review problems back in the lecture when I was going over the polynomials, because now specifically when it gets to solving a degree 2, it's a quadratic equation, but yes, I want you to understand this as a degree 2 polynomial. Okay, so I mentioned specifically in my lecture about the polynomials that yes, for quadratic, we have quite a few different ways, quite a few different methods to solve to find a solution for a quadratic equation like this. However, I would like to emphasize the method to solve this equation by factoring. Okay, because the factoring method will be the universal methods for any other polynomial equation. So another intention of mine is that I want any viewers or any student learning from this lesson is to see this equation not only as a quadratic equation, but also a polynomial, but generally as a polynomial equation. And that's where the factoring method is considered as the top priority, the most universal method. Yeah. Because, you know, when we step to something above degree 2, then really the factoring method is the only solution, the only method left for us to solve these polynomial equation. Okay, and so now that's enough emphasize here. By factoring this, okay, and assuming you're already fluent with your skill right there, then this polynomial on the left hand side, that which came out from our denominator there, we can factor that as x minus 3 and x minus 2. Okay, and I believe I don't need to mention about how I came up with those two factors right there. We should have seen this even before we enter this course, the pre-calculus course. Okay, and so now once upon successfully putting our denominator into factor form like this, and now we produce the same equation here. We produce another equation in the form of a product of two factors equals 0. Now once we arrive at this factor form on the left and then equals 0 on the right hand side, we can now go ahead and produce two separate equations where each one of them is one of the distinct factor. Okay, and that's the whole point about the factoring method being used in solving a polynomial equation like that. We're gonna pick each one of these a distinct factor in our factor product to set it equal to 0. So here x minus 3 is one distinct factor. I'm gonna create an equation x minus 3 equals 0. The other distinct factor is the x minus 2. So that becomes another equation, x minus 2 equals 0. Now, and that's what I meant by we're producing two separate equations here to find the values for x, because we had two separate factors here. All right. So now for this equation specifically, I am going to add 3 both sides. That gives me x equals 3. So we have found one of the bad guys. So this is our first bad guy that we found. This bad guy came out from that factor of our polynomial, our degree 2 polynomial. So x equals 3 is one bad guy. But what do I mean by one bad guy? Is there another one? Well, the reason I'm considering that is because we still have another equation to find, and who knows, we may find another bad guy. Okay, so x minus 2 equals 0. I'm going to add 2 from both sides, and that gives me x equals 2. So we found, here we go, I'm circling that in red, and we found another bad guy. So now it turns out we have 2 bad guys here. All right, so again, once we have finished solving our polynomial equation, purposely letting the denominator of our beginning rational function equal 0 and solve that polynomial equation, we will end up finding all the bad guys that we can. Okay, and now upon finding all of those bad guys there, these are the values, the x values that cause x squared minus 5x plus 6, that cause the denominator to equal 0. Okay, so now our domain is expressed as following. Now allow me to do another graphical explanation. On the line of numbers, increasingly from the left to the right, 2 is anywhere here, and then 3 is to the right. That's what makes sense right there. We got, these are the bad guys. So I want to take any other values. That's why I'm shading like that. I want to take any value on this line, just accept those 2 values. And now in old terms that, or in familiar terms that we have already learned from our polynomial lectures, then these bad guys, yes, we call them bad guys because they have something bad for our denominator, but in the end, generally as the solution out of this equation right here, we call these, back from our earlier lecture, these are the zeros of this polynomial, of the denominator, the polynomial. So these are the zeros of our denominator, the polynomial, because these values caused our denominator to equal 0. Okay, so once again I'm bringing back our understanding from the polynomial lecture right there. And then, or another way of saying that these are the horizontal intercepts of our denominator polynomial. Okay, so now but now back to the domain. The only way, it's just the way how it's just the way how rational function is. We just have to ensure that the domain is just any x values that we have to ensure the denominator is other than 0. So those x values are in the shaded part right here, but we have to exclude out the 2 and the 3. And that means now, as far as in interval notation, I'm going to take any values between -infinity and 2, but not taking 2. I'm going to take any other values, in between 2 and 3. That works too. And I'm going to take those values anywhere between 3 and positive infinity. So we have 3 separate zones where we can find an input that works for our rational function, but now excluding 2 and 3. And so now that's, and I'm using union signs like that. That completes our domain for this particular function like that. All right, so the similarity between the 2 problems I brought up as demos right here is we are going to have to start out by setting our equation, I mean, we're setting our denominator as a polynomial to equal 0. See, I set that x squared minus 5x plus 6 equals 0. On this board, our denominator was simply just that x minus 1. I set that equal to 0. And then upon solving that, we call those solutions the bad guys. Those zeros of the denominator, the bad guys. And then we're excluding out the bad guys. And then we're going to write our remaining domains right here in interval notation. So the domains are now as a bottom line, the domain for any rational function. The domain for any rational function is simply just any value. See, any values except, see this one right here, I just used that term earlier. This one, for this particular equation, it's the 0 of our denominator. Okay? And then these two values, 2 and 3 right here, the 2 and the 3, they are the zeros of our denominator. And so finally, as a generalization right here, for the domain of any rational function, we're just going to take any x values except the zeros of our denominator or our q of x. All right, so that's a generalization, and that's the common thing that, the final solutions of both demo problems came to agree about. I'm not saying that they have the same domain. See, this function has a different domain with the other function, but the way we find them is the same, and then the final conclusion is the same. We take any other values. We take any values anywhere except, and I use that term anywhere, so anywhere on the line of numbers here except those values being the zeros of our denominator. All right, and so now we are ready to put that into a formal generalization. Okay, a formal generalization. We can see that as a theorem or as a remark or as a conclusion, but then we use that, okay, as our main guideline for solving or for finding the domain of any other rational functions throughout the lecture here. Okay. So now let me erase this part of the board, and then we're going to write down that generalization as a conclusion here. All right, so now as a conclusion, all right, as a general conclusion, or you can also as a general conclusion or as a remark or whatever you want to say it, or as a recap. Okay, so generally as a conclusion, the domain of a rational function in the form of p of x over q of x. Okay, the domain of a rational function is anywhere, and I mean any x values. Okay, so the domain of a rational function p of x over q of x is anywhere but except. So now underline that word except for me. Okay, is anywhere except the zeros. Okay, except the zeros of q of x, because q of x is our denominator. So assuming our rational function is in that form already, a p of x over a q of x, then the domain is just simply any x value anywhere except the zeros of q of x. And that's how we tackle down the domain like that. Okay, and so now with this final conclusion, with this final general conclusion that we drew out from doing the two demo problems, the two demonstration examples here, now we are ready to use this. And so see, this is a formal general conclusion, but it's still circulating around that that major understanding. We just want to ensure q of x is non-zero. This is the major goal right here. And then because we want to serve that goal, we come up with techniques and methods, and then eventually an easier way to say is another way of seeing it is that the domain, the final domain, It's all because we want to ensure this. So consequently, the domain of any rational function is simply anywhere, any x values except the zeros of the q of x. All right, so it's now all connected. All right, so now let's get to the other board and get started into our examples. All right, so now we are at example 2, where we specifically focus to finding the domain of a given rational function. So the worded instruction is now going to become quite trivial. Find the domain of the given rational function. All right, find the domain of the given rational function. And so I am going to be giving out a few rational functions, and in each one of those will be the one problem in our example 2 right here, part A, part B, part C, and so on. Okay, so the first rational function here, and let's build our confidence through these example problems from the easy ones and keep rising the challenging level. Okay, and then we're going to keep rising up the challenging level right here. So R of x here, how about the first rational function in our example 2 here is x squared plus 1 over, how about 2x minus 6. All right, x squared plus 1 over 2x minus 6. And so x squared plus 1 is a polynomial. 2x minus 6 is also a polynomial. Okay, I'm not too particularly worried about or concerned about the degrees of these polynomials being involved in our rational function, because we're not at that stage where we need to worry about the degrees of those yet. But maybe it's good to be aware that the denominator is a linear polynomial, is a degree 1 polynomial. But that's all. Okay, so now upon realizing that our denominator here is other than just a constant, okay, then so that general conclusion we can use again in order to find the domain here, or another way of saying the domain of this rational function is just any x value anywhere except the 0 of this denominator polynomial. Okay, or another way of saying we just want to ensure 2x minus 6 is other than 0. We want to ensure the denominator is other than 0. Okay, that's another way of seeing it. And so in that way, now reflecting directly that general conclusion, we want to find, first of all, we want to find the zeros, because the domain is anywhere except the zeros of our denominator. So we're going to first start out by finding the zeros, or just maybe 1 0 of our denominator. So I'm going to purposely let the denominator equal 0. And then from here, the goal now is that the plan here is to solve for x. Okay, we're going to let the denominator equal 0. And we're going to solve for x to find the zeros of this denominator. So yes, from our understanding of a previous course, then we call this a linear equation, whatsoever name that is. But fundamentally at this point, I want viewers or anyone learning from this lesson to see this as we're finding the 0 of this polynomial. Admittedly, it's a degree 1 polynomial, but what we're doing here is finding 0 of a polynomial. And this specifically the denominator equal the polynomial of our rational function here. So 2x minus 6 equals 0. I'm going to add 6 from both sides. Okay, that gives me 2x equals 6. I'm going to divide by 2. Divided by 2 on both sides, that will land me into x equals 3. Okay, x equals 3. So I am not going to put that in a box and say that's my answer. This is not my answer of the domain. We want to find the domain. Okay, this is the 0. This is the 0 of our denominator. Or another way, like in that logical explanation I've made earlier, this is the bad guy for our rational function. It's bad in the sense that it will cause the denominator to equal 0, because that's what it is. All right, and that's why we call that it's a 0. All right, so make a good label of that, or just be fully aware that this is not our answer. This is the bad guy that we want to exclude it out from our domain. Okay, and so now let's make a quick sketch here. Let's make a quick chart here on the line of numbers. Okay, it never hurt to repeatedly get yourself into this habit right here. 3 is a bad guy. We want to take anywhere. See, in that logic, the domain is anywhere except the zeros. The 0 is here. We want to take anywhere except that 0. Okay, and so now upon seeing that, quick sketch, quick shading of the solution to this equation right here. Okay, and now we are ready to make a conclusion about our domain. Our domain for this function, the domain for this function is going to be anywhere except 3. So anywhere between negative infinity and 3. But see, it has to be completely parentheses. And then now union with the other interval anywhere between 3 and positive infinity. That is now our final domain right here for this particular function. And so I would like to highlight again, nothing was done with the numerator at all. So the work to find the domain of any rational function entirely depends on the work of finding zeros of the denominator. And then once we found the zeros, the bad guys that cause the denominator equals 0, okay, that's why we call those the zeros. Once we found all the zeros in the denominator, we're going to exclude them out from our domains, and our remaining x values aside from the zeros, that will form our domain right there. All right, and so nothing was done with the numerator. Let's now look into part B of our example, and we're going to start allowing these rational functions to become more challenging and more challenging, in a sense that the denominator will start taking us into those polynomials where it's more challenging to find zeros. Okay, so all right, so here we are at part B of our example. Our rational function here, r of x equals, now I have 3x minus 1, and I'm dividing that by, so how about x squared plus 8x plus 7. Okay, x squared plus 8x plus 7. So once again, this is a rational function in a sense that, yes, it's a fraction. We have numerator being a polynomial and denominator being a polynomial. This is our polynomial q of x in the denominator. And further, this polynomial in the denominator is other than just a constant. Okay, other than just a constant. Okay, it's an expression. It's a polynomial function that changes values depending on which input x value that we're giving it. Okay, and that is why we need to ensure being a fraction, we always need to ensure the denominator is non-zero. We need to ensure x squared plus 8x plus 7 is non-zero. Okay, and then that's why we had that general conclusion that the domain of this rational function is anywhere except the zeros of the denominator, Okay, so now we know clearly our goal is to find the zeros of the denominator. So now, for that plan right there, to serve that plan well, finding all the zeros of the denominator and then exclude it out from our domain right here, I highly recommend this practice right here. So now from, well, the earlier problem in part A right here, I didn't have to bother doing this because the denominator itself was already in a linear polynomial. Nothing to factor. But now with this one right here, we can factor our denominator before we even start tackling down the equation and find the zeros. And so now, in case your denominator is still in general form of a polynomial like this, it's a good practice, highly recommended to factor out the denominator, okay, into linear factors completely. So 3x minus 1 in the numerator stays the same, but now the denominator here initially or originally appear to be the general form. Now I'm going to, in factor form, I'm going to put that as x plus 7 times x plus 1. And again, I assume that anyone viewing this lesson is fluent with that skill, how at least decent enough, okay, or familiar enough with how to factor something like this in some quadratic into the x plus 7 times the x plus 1. All right, so now this step here is highly recommended before we start tackling down by letting the denominator equal 0. All right, so now it is clear that we need to let x plus 7 times x plus 1, our denominator, equal 0, because we want to find all the zeros first, okay, and then we're going to exclude them. And then we've learned from our lecture about the polynomials that as soon as we can put our polynomial in factor form successfully, where we have found some distinct linear factors, okay, then each of those distinct linear factors will be responsible for 1, 0, or one horizontal intercept of our polynomial here. So now that means I'm going to have x plus 7 equals 0, separately produced here. And this one here will be responsible for some 0. I will also have another separate equation, x plus 1 equals 0. All right, so x plus 7 equals 0. Solving for this, by subtracting 7 from both sides, I'm going to end up with x equals negative 7. And this is where I'm saying this x equals negative 7 is called the 0, one of the zeros of my denominator polynomial, my polynomial in the denominator here. Okay, so we have found 1 0, one bad guy. All right, so as far as the bad guy, okay, as far as the bad guy, I found 1. X equals negative 7. Okay, but now there's another one, because this we haven't done that x plus 1 equals 0 yet. We haven't solved that x plus 1 equals 0 yet. So subtract 1 from both sides. I'm ending up with x equals negative 1. So we found another bad guy. All right, so there's a bad guy here. So in this case right here, our denominator has 2 zeros. Or solving for the denominator equals 0, here we have found 2 bad guys. We have, for this entire function, there are 2 bad x values. There are 2 bad guys that cause the denominator equals 0. Okay, those are x equals negative 7 and x equals negative 1. So now let's put them on a chart and make some conclusion. The chart here is just simply the line of numbers from the left to the right. So negative 7 is somewhere on the line, and negative 1 makes sense to be to the right hand side somewhere. Okay, so now we want to see, the conclusion was saying we want the domain of this function is anywhere except these bad guys, except these zeros of our polynomial in the denominator. So I'm going to circle these two, and I'm going to be shading anywhere else. And that gives us a clear picture. Doing that will give us a clear picture of how we formulate our domain in final interval notation. All right, so domain. We have one from minus infinity to negative 7. That's one. We have another one between negative 7 and negative 1. Negative 7 and negative 1. And we're going to union those two disconnected intervals. They are disconnected in a sense that we took that out. We took out that x equals negative 7. We are not including that one. And then we have another one between negative 1 and positive infinity. Okay. And then I use a union here to connect those last two intervals. So now this is our total domain right here in interval notation, our overall final domain right there. All right, and that is how I have solved that particular problem here in terms of finding the domain of that rational function here. All right, let's now look at another example. So once again, this general conclusion I brought up here is extremely important. I've been using that twice, right? I've made that general conclusion and I've been using that twice throughout my the example problems like that. So once again, I emphasize the domain of a rational function in that form p of x over q of x. It's just simply anywhere except the zeros of the q of x. So all we do, so now yes, this is the beginning ultimate philosophy right here, but we don't even have to remind ourselves this anymore when we're doing these formal examples. Just the first step starting out is to set the denominator equal 0 because we want to find the zeros here. And once we have found all the zeros, we're going to exclude out the zeros, and all of those values after excluding the zeros of the denominator here will be our final domain. Okay. All right, so now let's arrive at our example 2, but part C here. All right, so part C. Okay, so our function here, how about r of x is equal to, now let's look at x squared plus 5x plus 6, and I'll have x cubed minus 7x squared plus 12x. Okay, x cubed minus 7x squared plus 12x. That's my denominator. So clearly speaking, this is my rational function at the beginning point right here. And then this is a polynomial. The denominator is also a polynomial. And further, the polynomial in the denominator here is other than just a constant. Okay, and that's why we have that need to find the domain of this function here specifically, because there will be values that cause the denominator equals 0, and we call those the zeros of our denominator. Okay, so now just like that, before I start tackling down the domain right here, I highly recommend rewriting our rational function in a way that we factor out our denominator. Okay, so I brought this problem in to remind you your skill, just to remind you your skill about how you can factor. Here in the denominator, I recognize a common factor. Okay, so let's do that. So r of x here is the first step. I recognize I have a common factor, so I can pull it outside. And then, of course, supposedly we have x squared minus 7x plus 12 remain in parentheses. Nothing will need to be done for the numerator. So I'll leave it there. But the denominator at this point right here, all of a sudden, if we focus specifically for this, the second degree polynomial inside the parentheses here, I realize that I can even factor this further, so that I can completely have the one linear factor and two more linear factors here. Okay, so we need to completely factor our polynomial in the denominator, any of our polynomial in the denominator before we get started. That's a common, good, highly recommended practice right there. Okay, so notice that x squared minus 7x plus 12 can be factored as x minus 3 times x minus 4. We have two distinct linear factors here that factor out from that quadratic. And so now I'm going to say the polynomial in the denominator finally turns out to be x times x minus 3 times x minus 4. All right, so that's how I have completely factored my denominator polynomial. Okay, and so now with this denominator being factored, with this denominator polynomial being completely in factor form right here, now we recognize this is a linear factor x minus 0. This is another distinct linear factor being x minus 3. This is another distinct linear factor being x minus 4. Okay, so now I'm going to go to the other board and get the problem down right there. All right. So now to serve that general conclusion, to follow that general conclusion actually, I am going to, again, the domain is anywhere except the zeros of our denominator. So in that way, I am going to let our denominator, which is now in factor form, so x times x minus 3 times x minus 4. This is the advantage of factoring out the denominator before we get to solving it. I'm going to let this equal to 0. Okay, I'm going to let that equal to 0. So we let the entire denominator equal 0. We want to set the q of x, our denominator, equal 0, and find all the zeros because we want to ensure the denominator is not equal to 0. And that's why we have to do this and then find all the zeros, because those zeros are the bad guys, and then our domain will be anywhere except those zeros. So now, having this equation in factor form completely like this, and we know from our past experience that we can produce three separate little equations, three sub-equations separately. So one of them is easily x equals 0, which needless to solve. Well, I mean, needless to work any further. We know that the answer here is x equals 0. It's one of the 0. Because x equals 0 will cause this left-hand side expression here to completely equal 0. The next distinct factor here is x minus 3 equals 0. Okay, with this one here, solving for x, I'm adding 3 from both sides. We have x equals 3. All right, so I found this is 1, 0, 1 bad guy. This is 2 bad guy. Okay, so these are the bad guys so far. Will we be able to find some more? Okay, we found one. So we've learned from our polynomial lesson, the lecture, that as long as we factor out completely our polynomial, then how many distinct linear factors there will be giving us that many 0. So that means we have another distinct linear factor there, x minus 4. So x minus 4 is equated with 0. Now adding 4 to both sides, that gives me x equals 4. Okay, and this is our third bad guy. So now we ended up with 3 bad guys. Okay, and so now with these 3 bad guys, we formally call them, these are the zeros of our denominator, of our x times x minus 3 times x minus 4, or in general form, the denominator is x cubed minus 7x squared plus 12x. Okay, and so now I am going to draw the line of numbers. So we found 3 bad guys. Okay, and so increasingly from the left to the right, because this is the line of real values right here. So 0 is one spot, 3 is another one, and 4 is another one. I may be upscale, okay, but we found 3 zeros. So now I'm going to shade anywhere else, because that's what the general conclusion I erased away said. It said that we're going to take just anywhere, the domain of any rational function is anywhere except the zeros of our denominator. Okay, so we're shading anywhere here except 0, at 0, except at 3, except at 4. All right, so that sketch now, that chart now, that shaded graph right here is giving us the direct the answer to our final domain in interval notation. It gives us a perfect indication of how we can come up with our final domain in interval notation. So we have one interval between negative infinity and 0. That's one of it. We have another one between 0 and 3. That's another one. We have another one between 3 and 4. And we have finally another one between 4 and positive infinity. Okay, so now union, union, union. That is our domain. All right, the domain is simply for this rational function, the domain for any rational function. This rational function or any other one that we have done previously, the domain of a rational function is anywhere, any x value except the zeros in our denominator. So the zeros came out from these distinct linear factors of our denominator. So the factoring methods, and specifically factoring the denominator, is extremely important because it indicates for us immediately the zeros of our denominator, and those will be the values excluded from our domain. Okay, now I'm not stopping our example 2 here yet. So let's do a couple more for you to gain better experience. Okay. All right, so now let's look at part D of our example over here. So now I'm going to give a rational function where the denominator has already been in factor form. Okay, so it saves us a little effort like that. All right, so how about in factor form? Our denominator is x minus 1 times x plus 2 squared. Okay, and then our numerator here is x cubed plus 2x squared plus, and I mean 4x squared, okay, plus 4x. All right. X cubed plus 4x squared plus 4x. Okay, so now to find the domain, nothing needed to be done with the numerator. And so that's why the numerator being in general form like this or being in factor form at this point in this kind of problem, finding the domain is not important. Okay, but the numerator here, but the denominator here being in factor form significantly saves us a huge amount of time. Because with something like this, we can easily identify the zeros here. It saves us that effort of finding the factor form of our denominator. So anytime we're finding the domain of a rational function, working on the denominator is our primary goal right there. Okay, and then factoring is the universal step, the primary work right there, the big step of the work, but it's all saved for us here because this polynomial in the denominator is already given in factor form like that. So in that terminology we've learned from the polynomial lecture right here, then with this particular linear factor, it has a multiplicity being 2 right here. So we have a linear factor x plus 2, but it's a multiplicity 2. That means this entire complete factor form of this denominator polynomial has really 3 factors. There's a x minus 1 and x plus 2 times x plus 2. So there are 2 identical factors here. That's why it's multiplicity 2. It appears twice in our denominator. However, as far as the distinct linear factor that's responsible for the zeros of our denominator, we only have just 2. X minus 1, that's one of them, responsible for x equals 1 later on. X plus 2 is another one. That's responsible for x equals negative 2 as another 0 right there. But we only have 2 distinct linear factor, and consequently ending up with 2 distinct zeros right there. All right, so let's get to it. So now I'm looking at, so really when we're just finding the domain, then my point of bringing up this problem is sometimes you may see a distinct factor but come with some multiplicity. That should not be anything that alter our the conclusion about the domain. Okay. So now x minus 1 is one distinct linear factor. I'm going to set that equal to 0. And then solving that for x, adding 1 from both sides, that gives me x equals 1. I have found 1 0 of the denominator. And now x plus 2, I don't even need to do the square. It's just x plus 2, the distinct linear factor there. Because as far as distinct, even though it's repeated here, but as far as the distinct, we just need to pick that once. So now I'm going to subtract 2 from both sides. That gives me x equals negative 2. All right. So just like that, this is 1 0. This is another 1. So we have 2 zeros for this entire denominator. Nothing was done with the numerator at all. Okay. And then so these are, again, if we want to keep calling it that way, these are the bad guys in the sense that they will cause our denominator to equal 0. And that's why we want to take them out. We want to exclude them. Okay, so now I'm going to quickly sketch the line of numbers. Okay, the line of all x values in real right there. Okay, so now increasingly from the left to the right, negative 2 is on the left, 1 is somewhere to the right hand side. And we want to be, so as that general conclusion was stating earlier, we want to take anywhere except x equals negative 2 and x equals 1. We take anywhere outside of, we take any value for x except these 2 because they are the zeros of our denominator. So in that case, now I am going to have, so how about one of them here is an interval between minus infinity to minus 2. I have another one between minus 2 and 1. And I have another one between 1 and positive infinity. All right. And 1 comma positive infinity. So now, and we use the unions that connects them. So this is our final domain. I just now realized that I didn't leave much room left for myself to write that word domain. Okay, so that's how we found the domain. But again, let's get into another problem to keep building your your confidence, okay, about doing these kind of problems like that. Okay. All right, so let's look at part E of our example. Let's look at R of x to be about x squared minus 5x plus 6, and I'm dividing that by x minus 2 r squared times x minus 1. All right, x minus 2 r squared times x minus 1. And so again, since we're about to find the domain of this rational function, nothing will be needed to be done in the numerator, because we only need to tackle down right to the denominator and find all the zeros of our denominator. And so now, thankfully, that big step for us is saved for us right here. Our denominator is already in factor form. So just right here, tackling down right here in this denominator, we recognize there are two distinct linear factors being involved. There was some multiplicity in that factor x minus 2, but as far as the amount of distinct linear factors, we have, these are just exactly just two distinct linear factors. So now in that way, I know that I'm gonna, okay, I know that I'm gonna have one distinct factor, and I don't even have to write that line let the denominator equal 0 anymore, okay, because we are well aware of that. So here I'm gonna just get straight into x minus 2 as one of our distinct, even though it has multiplicity too. Okay, but x minus 2 as a distinct factor, I'm going to let that equal to 0. X minus 1 as the other distinct linear factor, I'm going to let it equal to 0. And now I can solve for the zeros of my denominator here. The first one here on the left column, I'm going to add 2 from both sides. That equals x equals 2. That one on the right column right here, I'm going to add 1 from both sides. That gives me x equals 1. So these are the two zeros of our denominator here. Okay, so again, all we have to do is just focus. We've done, this is the 5th problem in our example 2, and including the 2 demo problems before we got into that formal example. So it's all about now, we're so firm that we just find all the bad guys or all the zeros of our denominator. Okay, so now these are the bad guys, and we found 2. Just the number of distinct linear factors. Okay, there may include, that's why I keep bringing up a few of these with the multiplicity, but it may include some multiplicity, but we only look for distinct linear factors. And so now these are the bad guys. We want to rule them out from our domain. All right, so now as far as the graphical picture right here, a graphical sketch right here, increasingly from the left to the right, 1 has to come first, 2 comes somewhere to the right hand side. Okay, we take, as far as the domain, we take any values except 1 and 2. All right, and that now gives us a clear picture of how we can formulate our domain in interval notation. So, one interval to the left of 1, which is the interval between negative infinity and 1, that's one interval. And we have another interval that we take anywhere between 1 and 2. And we have another interval that we take anywhere between 2 and positive infinity. And now with these 3 intervals, we're going to union them. We're going to put a union sign there. And that is our final domain. All right, that's our final domain with that in interval notation. All right.